Assalamualaikum and good day to all. So we will continue with the last learning unit, which is chemical equilibrium. Okay. So these are the learning outcomes that each and every one of you must accomplish. Okay. The first learning outcome would be defining the nature and characteristic of chemical equilibrium. So what are the characteristic of chemical equilibrium and what is chemical equilibrium? Secondly, explaining the significance of equilibrium constant and also reaction quotient Q. Thirdly, solving problem related to equilibrium constant in quantitative studies of chemical equilibrium. And then lastly, describing factors that will influence chemical equilibrium. So what is equilibrium? So you have covered kinetics, which is rate of reaction, how fast a reaction proceed. You have covered thermodynamics, okay, whether a particular reaction is spontaneous or not. Okay, so now we will look at equilibrium. Okay, so what is equilibrium? Specifically, chemical equilibrium. So it is the point at which the rate of forward reaction equal to the rate of the reverse reaction. Okay, so this is where the concentration of the reactant as well as the product will remain constant. Okay, so principally every chemical reaction is reversible. So if you have reactant A plus B to give you product C plus D, you can reverse it from C plus D to get A plus B. Okay. So in chemical equilibrium, the concept is it will only occur in a closed system at constant temperature. Means the temperature has to remain constant throughout the reaction. Okay. For example, you have a vessel here, okay, with water, okay, in liquid state and also in gas state. Okay. Make sure the temperature is constant. Let's say it's at room temperature. Okay. So the rate of evaporation, okay, the liquid state, okay, evaporate to form gas, will be equivalent to the rate of condensation where the molecule, the water molecule in the gas state, condense back to liquid state. So let's say if you have 6 molecules here, you also have 6 molecules here. So let's say one of the molecule here evaporate. So therefore at the same time, the other molecule in the gas state will condense to form liquid. So it has to be equal, so that it will remain 6 here and 6 here. Okay. So why it occurs in closed systems? So if it's in open system, how would the molecule will condense back? It will continuously evaporate without condensing. Okay, you won't get equal rate. Okay, so that's why the concept is it must occur in a closed system. So what are the conditions for chemical equilibrium? Okay, the constant observable microscopic property would be in terms of temperature, in terms of pressure, and in terms of concentration. You will look in this in much more detail in the later slides. Secondly, like I mentioned just now, it has to be in a closed system. Thirdly, must be at constant temperature, and it has the reversibility ability. Okay, and then the rate of the opposing changes are equal. One, like the previous example, one condense, another one would evaporate. Okay, so it has to be equal. So concept of equilibrium. Okay, it will help. For example, it will help to explain behavior of chemical reaction. Okay, and also buffer system. So that's why we have the equilibrium concept. So we can explain this behavior. Secondly, it can be used to drive reaction. that normally don't occur, or if it occur, it only occur to a small extent. Okay, so if you see this plot here, let's look at this second plot first. So concentration versus time. So as the reaction proceeds, the reactant concentration would decrease, and at the same time product will form. So that's why the concentration of product will increase. So until at one point in time, the concentration of reactant remain constant. So that's the product, and this is where it reach equilibrium. Now on the other hand, if we plot reaction versus time, okay, so if you see here, this is the forward rate, okay, this is the reverse rate, okay, reverse rate. At one point it will reach equilibrium. This is where the forward rate, okay, and the reverse rate are the same, okay, so this will be equilibrium. So this is example of formation of nitrogen dioxide from decomposition of dinitrogen tetroxide. So in terms of concentration, you would see the concentration of dinitrogen tetroxide will decrease over time, and at the same time increase in the concentration of nitrogen oxide, okay, because it will decompose to nitrogen dioxide, and at one point the concentration will become constant. So this is where the equilibrium will achieve, where it start to become constant. And again, if we plot the rate versus time, okay, this would be the forward reaction rate, this would be the reverse reaction rate. Okay, so this is the point where the rate become equal, okay, equilibrium. So note that you will see arrow pointing at both direction for chemical equilibrium. Okay, this double arrow would indicate that the reaction is reversible. Okay, so this form dinitrogen tetroxide decomposed to nitrogen oxide, and we can reverse this reaction from nitrogen dioxide forming dinitrogen tetroxide. Okay, so chemical equilibrium are dynamic. Dynamic means chemical change is still taking place. Okay, for example, the example on water just now in the vessel, in the flask. Okay, if one water molecule condense, another water molecule will evaporate, so it's still taking place. Okay, and it won't change the relative proportion. Okay, the number of molecule at both state remain the same. Okay, so example of chemical equilibrium are vapor pressure and solubility of solid in water. So as the reaction progress, okay, let's say we have reactant A here forming product B. So concentration of A would decrease until it become constant, and initially there's no product B, but then slowly it increase, okay, concentration increase until it become constant. The point where both A and B become constant, that is where equilibrium is achieved. So how can we relate concentration of product and reactant in any chemical reaction? Okay, we can write them in the expression we call equilibrium constant. Okay, so there are two types of equilibrium constant to express any chemical reaction. If the reaction involving gas, then we use Kp. If the reaction involving aqueous, then we use Kc. Okay, C indicate concentration, P would indicate pressure because it involves gas. So how do we write the expression? Let's say we have a general reaction here, A plus B, we get product P plus Q, and A, B, P, Q, small letter is the coefficient. So when we write the expression, okay, Kc, equilibrium constant in terms of concentration, so we use square bracket and the small letter become the power, okay, the coefficient. Now if it involve gas, okay, it's the same thing also. When you write the expression, you write it like this, okay, no square bracket because it involves pressure now, okay. Okay, so this is one example. Formation of carbon monoxide and oxygen from carbon dioxide. Okay, so we write the expression using Kp expression here. Okay, where the coefficient become the power in the expression. So let us look next at factor that will affect chemical equilibrium constant. Only one factor will affect the value of the equilibrium constant, which is temperature. And that is why in the earlier slide, you must have a direction must occur in a constant temperature. So if there's a change in temperature, then we would disturb the equilibrium. Okay. Factors that will not affect the value of a chemical equilibrium constant would be these three here, but it will affect the position. Only catalyst will not affect position, and we know the role of catalyst is just to speed up reaction. Okay, what it mean by affect position is whether it lies to the product side or it lies to the reactant side. So these are done experimentally. Okay, reaction between nitrogen and hydrogen to produce ammonia. Okay, note that the reaction are in gas phase. So there are 3 sets of experiment being conducted here, and each set will start with different concentration of reactant. Okay, so when we start with different concentration of reactant, we end up with different concentration of product. Okay, as well as the reactant after equilibrium has been achieved. Okay, and if we substitute this value in the expression here, okay, you will end up getting the same equilibrium constant value for every set. Okay, so note that the factor that are changed here is concentration. Okay, so concentration will not change the value of equilibrium constant, but temperature will do. So equilibrium constant K is the ratio of product to reactant. So therefore, if we have a large K value, it means more product present at equilibrium. And on the other hand, if we have smaller K value, it means there are more reactant present at equilibrium. So basically, if the K value is more than 1, it means product will dominate and the equilibrium will lies to the right. This is the point when we say it will affect the position. Okay, when we talk about when you involve factor of concentration or pressure. And if K is less than 1, then reactant dominate and the equilibrium will lies to the left. So go back to the earlier slide just now. The K value is less than 1. So it will indicate that the reactant will dominate the equilibrium and the equilibrium will lies to the left. Okay, so this is the Kc, okay, equilibrium constant for decomposition of dinitrogen tetroxide to nitrogen dioxide. So the value experimentally is 0.212. Okay, ratio of product to reactant. So if we reverse the reaction, okay, if we reverse the reaction means the reaction constant for the reverse reaction would be the reciprocal of the equilibrium constant for the previous value just now. So it will be 1 over 0.212. So the Kc value for reverse reaction would be 4.72. So there are two types of equilibrium. The first one is a homogeneous type of equilibrium reaction. So this means that all the reacting species are in the same phase. Okay, so look at this example here. Okay, the decomposition of dinitrogen pentoxide to nitrogen dioxide, both are in gas phase. So we can write the expression using Kc as well as Kp. Okay. However, in most cases, the value of Kc and Kp would not be the same. So to relate these two, we use this formula here. Okay, where R here is a gas constant, and this one indicates the change in number of moles. How to calculate the change in number of mole? You have to total up the mole of a product minus total of mole of reactant. For example, in this reaction here, okay, total mole in product is 2. Okay, total mole of reactant 1. So 2 minus 1. So change in number of mole will be 1. Okay. Alright, the next type of equilibrium is heterogeneous equilibrium type of reaction. So heterogeneous means the reactant species are not in the same phase. So meaning that more than one phase is involved. For example here, calcium carbonate forming calcium oxide and carbon dioxide gas. So note that these two are in solid phase, where carbon dioxide is in gas phase. So when we do the experiment, the amount of carbon dioxide here will not depend on the amount of calcium oxide as well as calcium carbonate. And why is this so? So if density or molar mass is a variable, then it would depend on the solid calcium carbonate and calcium oxide. Okay, but neither density nor molar mass is a variable. Okay, so therefore concentration of solid and pure liquid are constant. Okay, generally speaking, you cannot find concentration when something that is not in the solution form. Okay, so you cannot find concentration of solid. Okay, you cannot find concentration of liquid also. Okay, so you normally find the concentration in when it is in aqueous form, okay, or gas form. So in writing the expression, we will ignore concentration of pure liquid and pure solid. So that is why carbon dioxide here does not depend on calcium carbonate and calcium oxide. So we write the expression Kc, okay, only based on the carbon dioxide gas. So again, when we look at this reaction here, the solution of lead chloride solid forming lead 2 plus aqueous and chloride aqueous. When we write the expression, we do not put in the lead chloride solid. Okay, we only consider the aqueous form. Okay, similarly for this second reaction here, we don't put liquid form or liquid state of matter inside the expression. So look at this first example here. Okay, and the concentration of all of the species here is measured at equilibrium. Okay, which is the temperature involved is 472 degrees Celsius. So question is calculate the equilibrium constant at 472 degrees Celsius for this reaction here, formation of ammonia from nitrogen and hydrogen gas. So write the expression involving this reaction here and then substitute the equilibrium concentration inside the expression to find the Kc, which is equilibrium constant. Okay, substituting, do not forget to write the coefficient, okay, coefficient as the power. Okay, so the Kc value will be 1.04 times 10.1. Note that it has no unit, okay, because it's constant. Okay, the second example is based on this balanced chemical reaction, 2 moles of ammonia and oxygen, okay, means 2 moles of ammonia and 2 moles of oxygen, and then there are 3 moles of water, all are placed in one flask at room temperature, and then pressure is monitored as the reaction proceeds, okay, and until it reach a constant pressure. Okay, when it reach a constant pressure means it already reached equilibrium. So at this point, okay, when it reach equilibrium, there are 1.6 moles of ammonia. So the question is, what is the concentration of all substance involved? So means the ammonia, the oxygen, the nitrogen, and H2O. Okay. So how to solve this question? Okay. First of all, you need to prepare ice table. So this is the ice table for the reaction involved. Okay. So the question involve 2 mole of ammonia, 2 mole of oxygen, and 3 mole of water. So no information of nitrogen oxide given, so initially 0. Okay, and it was stated that the equilibrium of the ammonia concentration is 1.6. Okay, 1.6 mole. Okay, so we write that 1.6 mole here at the equilibrium. Okay, so based on this information, the ammonia concentration decreased by 0.4 mole. Okay, so how to find the rest? Okay, so for change, we use minus 4x. Okay, let me just. Okay, so this one would be minus 4x, right? So this would be minus 5x. Okay, look at the coefficient. I'm sure you already know this. Okay, this would be plus 4x, and this would be plus 6x. So how to find x? So 1.6, okay, minus 2, okay, divide with 4 to find x. Once we know x, we can solve for the others. Okay, and then use the volume given, which is the flask at 1 liter, to find concentration. Remember, this is only referring to moles, not concentration. Okay, so this has been calculated for you. Okay, where x is equivalent to 0.1. So substitute the value of x in each of the change value, so we can calculate the equilibrium. So because the flask use is only 1 liter, means the equilibrium concentration for every species is already reported in molar. Okay, so 1.6 molar, 1.5 molar, 0.4 molar, and 3.6 molar. So the third example here is reaction of carbon monoxide with chlorine forming phosgene, COCl2. Okay, so reaction here at equilibrium is each concentration equilibrium is given here. Okay, carbon monoxide, chlorine, as well as the phosgene. So question is calculate the equilibrium constant Kc and Kp. So you are asked to calculate both Kc and Kp. Remember the relationship between Kc and Kp. So Kc and Kp is related this way here. Okay, so first of all, let us calculate Kc because concentration are given instead of pressure. So we calculate Kc. Okay, don't forget coefficient if it involves coefficient. So since every species is 1 mole, okay, the Kc value is 220. Substitute this value into here. Okay, substitute the gas constant R, which is 0.0821. Temperature given, which is 74 degrees Celsius, but you have to write it in Kelvin. Okay, so plus 273. Okay, to find the change in number of mole. Remember, total mole of product minus total mole of reactant. So 1 minus 2, so negative 1. So n is negative 1. So Kp would be 7.7. Okay, the fourth example is reaction formation of bromide from bromine gas. Okay, bromine ion from bromine gas. And given the Kc value is this. Okay, given the temperature also. Okay, if the initial concentration of the species are given here, what is the concentration at equilibrium? So how to solve this problem? Again, to solve this question, we draw the ice table. So ice table is constructed here, given the initial concentration. Okay, and then the equilibrium, okay, for both species. Substitute this inside the expression, and Kc value is given. We can solve x. Note that in the denominator we have minus x. So when we expand this expression, we will get a squared plus bx plus c. Okay, so it will look like that. So to solve this, we might need to use the quadratic formula. Okay, so how to solve that? Okay, so when we use quadratic, we will get 2x value. Okay, when we get 2x value, we will take the x value that is more logic compared to the other x value. However, I think you already know this. Okay, we can simplify this expression here by assuming that this x value in the denominator is too small compared to the 0.063 value, so we can ignore this. Okay, so we don't have to solve using quadratic, okay, to find x value. Okay, so this shows that in order to solve for x, quadratic formula was used. Okay, so note that we have two to x value. Both are negative. So to find whether which one is more logic, we substitute them inside the expression. Go back to the early expression here, okay, to find the concentration. So for bromide, it's negative 0.09 m or positive 0.0844. Okay, when this value is substituted here, this value is substituted here, and this value is substituted here. Okay, for bromine, when this value is substituted here, we get 0.0735. When this value here is substituted in this x here, we get 0.6. So which one should we choose? Because this is negative, we take the second one. Okay, that is when we use quadratic. Okay. Okay, so this example will approximate instead of solving using quadratic, because when we make approximation, we will end up getting more or less the same value. So it's easier for us to approximate. Okay, so it means the previous example, you can try solving it by making approximation. Means the x in the denominator can be ignored. Okay, and see the value that you will get. Okay, it should be more or less the same with the quadratic approach. Okay, so in this example here, rather than solving it using quadratic equation, okay, we will approximate. Okay, so substitute expression, okay, and the Kc value, okay, to find x. So when we approximate, we can ignore this x value here. So it will become, okay, for x cubed equivalent to 1.6 times 10 negative 12. So solving x will be 7.4 times 10 power negative 5 molar. So it's easier we do approximation rather than solving quadratically. Okay, so let us substitute back the value of x that we get just now. Okay, so when we substitute back to find Kc, we get this value which is very close to the given value just now. So that will confirm that our approximation is okay. Okay, so this is summing up step by step that what you need to do when you solve problem relating to equilibrium constant. Okay, the first is making sure the chemical reaction is balanced. Okay, then you write the equilibrium expression. Okay, secondly, write ice table and fill in all the given amounts. Okay, and then use stoichiometry, okay, for the change in the concentration line, the second line of the ice table, this one, C. Okay, 4, reduce the equilibrium concentration for all species based on the all information given. Okay, note that usually the initial concentration of product is 0 unless it is stated like the second example just now. Okay, the water H2O. Okay, so it's given initially 3 mole present. Okay, if it's not stated, then normally 0. Okay, next we move on to reaction quotient Q. So what is the difference between Q and K, the equilibrium constant that we have calculated? Okay, Q means the reaction indicate that the reactant and product are not at equilibrium. Okay, so that's what I mean by Q. K means it's at equilibrium. Q means it's not at equilibrium. Okay, so that's why we name them name it as reaction quotient. Okay, So similarly like K, okay, we write the expression of Q the same way. Okay, but the concentration of the species are at any time, any point in time. Okay, as long as it is not at equilibrium. So we can predict the direction of the reaction, okay, by calculating the reaction quotient Q. Okay, so how to do this? Okay, so if Q is less than K, okay, if Q value is less than K, then the reaction, forward reaction must occur in order to reach equilibrium. Okay, if the value of Q is the same as K, means the system is already at equilibrium. And if the value of reaction quotient Q is more than K, so that means reverse reaction must occur so that the reaction will reach equilibrium. Okay, now let us look at this reaction here. Okay, Kc is given, okay, at this temperature of 100 Kelvin, and the concentration of every species is given. Okay, so determine whether the reaction is at equilibrium. If it's not at equilibrium, in which direction will the reaction proceed? So go back to the concept just now. If Kc is more, is reaction Q or quotient Q is more than Kc, so that means the reaction has to reverse. Okay, if the Q is less than K, then the reaction must go forward. Okay, so we are given the concentration of the species, and then we compare with the K. So I'll substitute this in the expression to find reaction quotient Q first. Then we compare with Kc. Okay. So substitute the concentration given. Okay, so the Q value is 4,700. So this value compare with the Kc given just now. It's larger. So what does this mean? That the reaction is lie more on the product side, so it will have to go to the left, okay, making more reactant. Okay, so the reaction will move to the left, making more reactant in order to reach equilibrium. Okay, so based on the equilibrium constant value, okay, if K is more than 1, then the reaction is product favored. Okay, so product will predominate at equilibrium. If K is less than 1, then the reaction is reactant favored. Reactant will predominate. If the value of K is very small, it means that reaction is not likely to happen because too small. Okay, however, if the value of K is too large, okay, it means that reaction is feasible. Okay, the reaction can proceed. So next we move on to Le Chatelier principle. Okay, what does Le Chatelier principle means? Okay, it means that the system will respond by shifting to reactant or product, okay, when the equilibrium is disturbed. Okay, and this principle will guide us to predict the effect of various change to the position of equilibrium. Okay, these are the factors that can disturb the equilibrium. Okay, change in concentration, change in volume, change in pressure, change in temperature, and addition of catalyst. Okay, so based on Le Chatelier principle, if a chemical system at equilibrium experiences a change in concentration, temperature or total pressure, the equilibrium will shift in order to minimize the change. Okay, so it is named after a French chemist named Henry Louis Le Chatelier, and his principle was used by chemists to manipulate outcome of reversible reaction, okay, so that yield of reaction can be increased. Okay, so it was proven that nitrogen containing substance can stimulate growth of field crops, so means a good fertilizer. So back in the 19th century, nitrogen rich fertilizer was used from bird manure, but it was predicted that at one point the world will run out of shortage, okay, of nitrogen. Okay, so therefore Haber developed, okay, a method to produce ammonia from its element. Okay, so Haber is a physical chemist, okay, and he won a Nobel Prize, okay, in 1918 for the synthesis of ammonia from its element. Okay, so manufacture of ammonia is a good example which apply both kinetic and equilibrium. Okay, so if you remember in the previous lecture, the factor that will affect the value of equilibrium is temperature. So that's why when we increase the temperature of this reaction here, okay, the value of equilibrium constant will decrease. So when it decrease, eventually it will go less than 1. If less than 1 means reactant dominate, and we don't want that because we want product. Okay, so therefore two things can be done, okay, so that we keep on producing ammonia. Okay, so means the reaction is product favored. Okay, first, pressure. So we increase the pressure. When we increase the pressure, remember one of factor that will affect position but not equilibrium value is pressure as well as concentration. Okay, so pressure will affect position. So when we increase pressure, the reaction will favor to the product side, forming more ammonia. Okay, another thing that can be done is addition of catalyst. So remember, kinetically, catalyst will speed up reaction, but it will not interfere with the reaction itself. Okay, so add ion catalyst to the reaction will speed up the reaction to form ammonia at a faster rate. Okay, so an effective catalyst for Haber process is ion tetroxide, okay, Fe3O4, mixed with potassium hydroxide, silicon dioxide, and aluminum trioxide. Okay, and because catalyst is not effective below 400 degrees Celsius, the process is carried out at this range of temperature, okay, 400 to 450 degrees Celsius. Okay, now let us see the effect of concentration change to the Haber process. Okay, so the reaction involving nitrogen and hydrogen to produce ammonia. Okay, let's say this reaction here has reached equilibrium. So this is the initial equilibrium, okay, where the concentration remain constant. Now, when we disturb the equilibrium, means we change in the concentration of the reactant, or we play around with the product, we will change the initial equilibrium to a new equilibrium. Okay, so it will reach a new equilibrium if we play around with the or we change the concentration of the reactant or the product. So if we add reactant or product, okay, it will shift the equilibrium away from the increase. Remember, Le Chatelier principle is to minimize change that occur. Okay, so we add reactant, for example. We add reactant, so this will have more in terms of ratio. Okay, so to decrease this, it will shift the equilibrium to form more product in order to compensate the addition of the reactant just now. Okay, remember, it shifts the equilibrium away from the increase. So this will increase to make sure it decrease for more product. So you shift to the product side. Okay, if we remove a reactant, okay, let's say we remove nitrogen. Okay, so the equilibrium will shift towards the decrease. Okay, so because this is decrease, let's say we decrease the concentration of nitrogen, so equilibrium shift to the reactant side, forming more nitrogen to compensate the decrease just now. Okay, so that is Le Chatelier principle. Okay, so because of this principle, we can manipulate reaction, whether we want to form more product or we want to form more reactant. Okay, so to optimize the amount of product at equilibrium, we need to flood the reaction vessel with reactant and continuously remove the product. Okay, so let's say we add more nitrogen and hydrogen, it will produce more ammonia. But if we don't remove the ammonia, it will shift back the equilibrium back to the reactant side. So once it form ammonia, collect it, continuously add this, so that it will continuously form product. Okay, so that way we can optimize the product. Okay, based on the Chatelier principle. Okay, so the Haber process will optimize the formation of ammonia product because it is continuously removed and the reactant are continuously added. Now let us see the effect of volume and pressure change. Okay, so we decrease volume, we will increase pressure. Okay, so according to Le Chatelier principle, if pressure is increased, the system will shift to counteract the increase. Remember, pressure is one of the factor that will change the position of the equilibrium, but it won't change the value of equilibrium constant, but it changed the position. So according to Le Chatelier principle, if the pressure equilibrium is disturbed, it will counteract the disturbance. Okay, so if pressure is increased, okay, the system will shift to remove gas to decrease the increased pressure just now. Okay, so increase in pressure normally will favor the direction that has fewer mole of gas. So you have to compare the mole of product and reactant. Which side has less mole of gas? Okay, so increased pressure, it will move to the direction that has fewer mole of gas. Go back to the Haber process. Haber process, 1 mole of nitrogen react with 3 mole of hydrogen. So total 4 mole, forming 2 mole of ammonia, only 2 mole. So product side only have 2 mole, reactant side have 4 mole. So that's why we increase in pressure, so that the equilibrium will direct to the side that has fewer mole of gas, which is the ammonia side. Okay. However, if the product and reactant both have same number of mole, you increase pressure or you decrease pressure, it will have no effect. Okay. Now let us see effect of temperature. Okay. So temperature will change the value. Okay, it's the only factor will change the value of equilibrium constant. Okay, so if we increase temperature, it will favor the endothermic process where the K value will increase. Okay, so if we decrease temperature, K will increase for exothermic reaction. Okay, now go back to the Haber process. Okay, to see the effect of temperature. So like I mentioned earlier on, okay, this reaction is exothermic and product favored where K value is more than 1. Okay, because that this exothermic reaction is slow, okay, at room temperature, so it is carried at higher temperature to speed up the rate reaction. Okay, so when we speed up the reaction by increasing the temperature, this value of K, equilibrium constant, will be lowered. Okay, when it's lowered, it would not favor formation of product, but it will go to the reactant side. So that's why this reaction needs to have pressure as well as catalyst. Okay. Okay. So this one has been explained just now. So equilibrium will shift to the left when we increase the temperature. Okay. So what happens when temperature is reduced? Okay. When temperature is reduced, it will eliminate the heat from system and it will shift the equilibrium forward. Now, to understand temperature effect, we assume heat is as one of the reactant. Okay, one of the reactant. For example, have reaction of nitrogen, okay, sorry, nitrogen and oxygen, okay, forming nitrogen oxide. Okay, and this reaction, okay, the enthalpy change for this reaction, okay, enthalpy change for this reaction would be endothermic. 180, sorry, 0.6 kilojoule per mole reaction. Okay, reaction. Okay. Now, let's say we increase the temperature of this system here. We increase temperature means we're adding heat. So let's say we add heat, so heat will serve as reactant. So based on Le Chatelier principle, when heat is applied, it will counteract, right? So heat is added, so it will proceed to the formation of nitrogen oxide in order to reduce the heat. Okay. So what happened if temperature is for exothermic reaction? This is endothermic. Now let us look at exothermic reaction. Let's say we have this reaction here. Remember, dinitrogen pentoxide decomposition forming nitrogen dioxide. We reverse with that reaction. Okay, we reverse that reaction so that it become exothermic. N2 of, so the enthalpy of the reaction change would be negative 57.1 kilojoule per mole reaction. Okay, so because this is exothermic reaction, means heat is being released. So when heat is being released, it will be in the product side. Okay, heat. For the endothermic process like this one just now, heat is in the reactant side because this reaction absorb heat. Okay, endothermic. Okay. Now, if we lower the temperature for this reaction here, the second one, we lower the temperature. So what happened when we lower the temperature? We remove the heat. Right? Okay, so when we remove the heat, the system will counteract this effect by forming more nitrogen pentoxide, so that it will form more heat to counteract the decrease in the temperature of the system just now. Okay, so that's why K will be larger at lower temperature. Okay, for exothermic process. So this one is actually explaining the table in the previous slide. Okay. Okay, basically, if the reaction is endothermic, we add heat will favor the forward reaction, so we move to the product side. Okay, if the reaction or the system is exothermic, okay, adding heat, okay, will favor the reverse reaction. Okay, so that's why we lower the temperature so that it will favor the forward reaction, like the example I gave just now. Okay, so we remove heat, okay, for exothermic process so that it will favor the forward direction. Okay, and we remove heat. If we remove heat for endothermic process, will favor the reverse reaction. So if endothermic, it will favor the forward reaction if heat is added. Okay, you remember one, the other one will be the opposite. So if, okay, to avoid getting mixed up or confused. So next we will see the effect of catalyst to a reaction based on the Chatelier principle. So catalyst only act to speed up reaction. Okay, it itself does not being consumed or affect the reaction itself. Okay, it only speed up, okay, the reaction. So kinetically the reaction is faster. Okay, so this is uncatalyzed reaction, so you see the activation energy is rather high, but when we add catalyst, okay, the kinetic energy is the activation energy is reduced. Okay, so catalyst will lower the activation energy for both the forward and reverse reaction. However, it does not change the constant value or disturbing the position of the equilibrium. It only speed up the reaction. Okay, so this is the sum up of the Haber process. So based on the Chatelier principle, to maximize the formation of ammonia industrially, okay, keep on adding the reactant continuously and at the same time keep on removing the ammonia as it form. Okay, use high pressure because high pressure will favor to the side that has lower number of mole, in this case 2, this one is 4. Okay, so high pressure. Okay, we cannot use low pressure, low temperature, because too slow. Okay, too slow, so we increase the temperature, but increasing temperature will favor the reaction to be reverse. So therefore we use temperature that is good enough to optimize the formation of ammonia. Okay, so 400 to 450 is recommended. Okay, and of course adding catalyst, okay, which will speed up the reaction.